autoscaling, and how you can use KEDA using how you can scale your application using the KEDA. So that is what the topic which I'm going to cover today. Just a quick background about me. So I have 16 years of experience in software development, and currently I'm working as a principal engineer with Arcesium, which is a financial services based company. I have many, I have certifications in AWS and all Kubernetes certification, including the latest KCSA as well. Now, coming to the contributions, I have made some open source contribution also. We have Terraform from HashiCorp, as well as the CNCF projects like KEDA, as well as things which Satyam was talking about, which is the incubation project. So here is the agenda which I'm going to talk about today. So the initial 2 slides is going to be a brush up for most of you guys, where I'm going to drill down and why the scaling is important, be it monolithic applications or the microservice-based applications. So you will come to know the nuances of the scaling on those. Then I'll get into the autoscaling Kubernetes and its types, followed by the HPA, which is horizontal pod autoscaler. There will be a demo for HPA. And then we'll have a deep dive session into the KEDA, which is a Kubernetes Event-Driven. So there will be a demo for KEDA as well. And finally, we'll wrap up with some reference links and key takeaways for this. Now, coming to monolithic applications. Now, some of you might already have experience in the past also while building the monolithic applications. Now, whether you go for any monolithic applications or the microservices applications, 2 most important things which you have to consider while designing the system. A, that is, the system should be highly available in nature. During any failure, the system should be able to fall back to the secondary applications and serve the customers. But first, which is HA, which is high availability. Second one is the scalability. And so system should be able to scalable to meet the network traffic. So if there is a load in the application, so your application should be able to adapt and serve the customers. There are other trade-offs also. The cost, of course, is one of the factor at fault tolerance, but that is out of scope. But these are the 2 main factors when you design a system. Now, coming to the monolithic applications, right? So let's say, for example, if you have, let me take the example, right? So let's say, for example, if you build one e-commerce site, Amazon.com, using the monolithic-based approach. So what you're going to have, you will have this, this presentation layer business, now everything packaged together. So, as a single artifact. So if you're talking about the Java, you will end up using this WAR file. If it is Kotlin or Java, you will have this WAR file. Then you will deploy this onto a particular server. This is JBoss or Tomcat, right? So this is how you are going to follow with the monolithic-based application. But there are some drawbacks for this. Let me just talk about the easiest thing. When it comes to monolithic applications, the best and easiest thing is you can go and it's very easy to deploy. You don't have to worry about anything. There are not much cost also associated with this. Because you have a single package which you are going to deploy onto the application server. If something goes bad, you know which is your source of truth. You have just single log to trace the errors. So debugging is much easier when it comes to monolithic-based applications. However, you have problems when it comes to monolithic-based applications. You will not be able to scale. Just imagine you have built an Amazon.com. You have different functionalities, like you have warehouse, you have products, you have the payment system, everything clubbed together. If you want to scale your application, which is a monolithic Amazon.com, you have to scale the whole application altogether, which results to a wastage of compute resources also. And if there is any outage, the whole application will be down. And the worst thing is that if you want to change a single title also, you have to rebuild everything, you have to deploy the whole WAR file, so which impacts the whole application account. So this is a problem with the monolithic-based application. They are very difficult to scale. Now we'll see how your microservice-based applications are going to help you with. So in this diagram which you see here, right, this is one example over here. So here, let me take the same example of the Amazon.com. So let's say, for example, we have just 100 users, total 100 daily active users on Amazon.com. Now this one we have built using a microservice-based approach. where each and every component is acting as a microservices here. The best thing that we can do over here is we can scale each and every microservices based on the need. So let's say, for example, if there are out of 100, let's say 90 users are there who are browsing the products or just adding the products to the cart. But there are remaining 10 users who have already decided their mind. Now they are about to make the payment. But let's say if this my payment service is down, your whole application is not down. All the users who are was about to do the payment, only some set of users are impacted. So your remaining application is still up and available. Let's say even if it is not 100% availability, you may have let's say 95% of availability. This doesn't give any bad impression rather than monolithic, where your whole application is going down. So there are some advantages also when it comes to microservices. Means you can scale out and scale in your application based on different matrices. We can talk about CPU memory later, but based on different metrics also it can scale. Plus you can run each and every microservices with a different capacity needs. Means if you think your payment is going to be bombarded during any let's say Black Friday season and all, you can upsize it, or you can have more underlying capacity also. So that's what your payment you can upsize a particular microservices. Plus, like already talked about the near zero downtime, means your whole application is not down in case of microservices. But there is a flip side of it. The flip side is when it comes to microservices, costing is very high, which is not the case in monolithic applications. And the reason why the costing will be high is because when we talk about the microservice-based applications, if you have to debug something, let's say your request is going in a format, let's say GUID, that request will go to various microservices. You need to have proper application monitoring systems, let's say Datadog or Prometheus. You need to have additional systems to monitor your applications. So costing is a bit higher when it comes to microservices, but that is a trade-off. Plus the logging maintenance is a bit overhead when it comes to monolithic-based applications. But you can scale your microservices very well as per the need. Now you have your microservice right with you. Now how you are going to deploy your microservices? Traditionally, what we do, we'll just go and create a Docker file, and that Docker file will, you will just go and have base images. This is one dynamic representation of a Docker image. You will build your Docker image, and then you will go and deploy it. And where you're going to deploy your Docker image, let's say you will use some kind of container registry. You can use AWS ECR, you can use JFrog, anything. You have your Docker image with you, right? So, and in order to deploy that Docker image, your application in the end of the day on a particular server, what you will do, you will just go and do the Docker pull. And I'm not talking about the orchestration tool like Kubernetes here, but in a plain scenario, you have an image, you have microservice, you have an image, you have pushed that image to a particular container registry. Now, in order to do the deployment, in the end of the day, you can use some Docker tool and it will get deployed to a particular server. Now, if you have some kind of, superpower, or let's say if you can predict the traffic upfront, let's say your own algorithm, you think, okay, my December, January, the traffic is going to be higher. What you can do without using an orchestration tool or Kubernetes here, you can go to login to the server, you can create a Docker run again. You can spin up any additional containers by yourself, man. You don't need any Kubernetes at all. So you can make the system highly available. If one container goes down, other container will serve the traffic for you. So that is how manually you can do. And if you want to down, you can obviously go and kill the containers. But Kubernetes is a solution for you. What Kubernetes will do, if you instead of doing that Docker pull or everything, right, it will automate your whole deployment process by itself. So Kubernetes is best when it comes to scale out, automatically scaling based on some the metrics which we are going to discuss about. Then Kubernetes you can also use it for applying the resource quota. Let's say for example, if you think I have 8 virtual CPUs of my underlying server, if you want to restrict it, I don't want my pod to consume all these, you can have the resource quota applied on the pod level so that it doesn't exceed, let's say 2 vCPUs anything. So that's what the this resource code I talk about. And then you can apply the best practices, best security practices in the Kubernetes using the least principle of access. You want to restrict, you don't want everyone to access your cluster, you can restrict it. You can have proper role-based access control over here so that no unauthorized access can be made over here. Plus, obviously, all the API calls to the Kubernetes clusters are audited and they are all stored in any etcd cluster. So this is a diagrammatic picture like how a pod is going to look like when it is deployed to the Kubernetes environment. So traditionally, you can have the basic, the smallest unit in a Kubernetes is a pod. That's the minimum unit, right? So in order to make the replicas of that pod, you need to have some kind of other Kubernetes object, like the deployment, or let's say you need to have some stateful set or something. So you can create a deployment, and then you can have multiple replicas within that. So you can have one pod. So if you see here, we have one pod. So that's as per you can have one pod as equals to one container, or you can have multiple containers within one pod. But the ideally, the approach, the best practice is to have one pod is equal to one container. Okay. Then the last point is what your deployment, like we are talking about the deployment here. So what the deployment can do, whatever the desired replica count you are going to do. So Kubernetes will maintain that throughout the lifetime of that pod. So it will maintain that. So if you see this example, so we have a single container. So this is a pod that has single container web application. When scaled out, so we got additional pods. So pod 1, pod 2, pod 3 got created. So that was a need. Now, let's talk about the auto scaling in Kubernetes. Now, Kubernetes is intelligent enough to auto scale based on the needs. Broadly, there are three types of autoscaler available within the Kubernetes. So, first one is the vertical pod autoscaler, which is VPA. Second one is the cluster autoscaler, which is CA, and the third one is the HPA. Now, this is about the VPA. So, how the VPA will work? For example, you have a pod. Instead of doing the scale out and scale it, you want to upsize it. You don't want to have additional cost. You just want to upsize it by adding more CPUs or memory. You can use the VPA for that. So there are different modes of it. Let's say recreate initial, but these are beyond the scope of today's discussion. I'll park it for some other session. But if you see here in this example, we have a database which is Postgres running, and initially it has two cores. When we upsize it using the VPA, we are using the same pod with our Postgres, and since it's a database, we have to maintain the state, otherwise we end up losing the data, right? So we have upsizes from 2 cores to 4 cores, and same for memory also for 4 GB to 8 GB, using different modes available. Of course, not the recreate one, because it will kill the database and it will create a new database, which we don't want it. So that's about the VPA. So second one is the cluster autoscaler. Now I request everyone just to follow. I want to emphasize more on this, which is the controller manager and scheduler, as they help doing the cluster autoscaler. Now this is a typical internal architecture of a Kubernetes. Now if you see here, this is a 3-node cluster. We have a 1 master node. We have a 2 worker nodes over here, and the brain behind the Kubernetes is the API server. Whenever you interact with the Kubernetes, your API server is the first one, which is going to get the request and interact with other components also. So we have, let me just quickly brush up. So we have the kubelet. Kubelet is responsible for pulling the Docker pull. The one which I told you can go manually. So kubelet is the one which is going to actually do the Docker pull from the repository. We have HCD, which is responsible. It's a database which is responsible for storing the the audit policy. All kinds of interaction will be stored in the HCD. We have kubeproxy for networking, for pod networking. Then we have the controller manager scheduler, which are very critical. Now, controller manager has a responsibility in the Kubernetes cluster. So if you, in your pod, if you define, okay, I need to have my application with 5 replicas, and it's the job of the control manager to meet that demand. So whatever your replica count is there, so control manager is going to need that. If it is not fine, it will make the actual state also as a desired state. That's the responsibility of the control manager. Then coming the scheduler. Now, it is the responsibility of the scheduler to identify the right worker node and then do the deployment. So then if you tell, okay, this is my worker node, right worker node, the next pod should be scheduled on this particular worker node. So that decision is taken by the scheduler. Now, what will happen, let's say for example, why C is very important here is, let's say for example, you have, Kubernetes has already scaled many pods, right? Now, there are not much enough space left in any of these two worker nodes, right? So, what the CA will do, CA will kick in. It will go and provision additional worker nodes that will become the part of the cluster. So assume you will have worker node 2, which is an existing one. CA will provision additional worker node, and then this scheduler will go and schedule that pod into the new worker node. So if the pod is not scheduled for some reason, let's say the underlying capacity is not there enough, so pod will come into the pending state. So there are different status also. Let's a pod goes to the container trading and all. It will go to the pending state. But the moment the new worker node has been provisioned, the pod will come into the running state. And who is going to do that? Of course, the kubelet. So kubelet is going to pull that image from the Docker hub or wherever you have pushed your Docker image, and it will start your application in that worker node. So that's the responsibility of the CA. Now, okay. Now, the last one is the HPA, which is horizontal pod autoscaler. So, we have talked about the VPA, which is responsible for upsizing. Now, the HPA is responsible for doing the scale out in a horizontal way. It will add additional pods that is scale out, and it will scale in. When there is no need, it will start removing the pods also to meet the network demand. So how this is going to work, HPA, the primary metric, not the primary, the only metric which HPA depends on is the CPU and memory, nothing beyond that. So based on the CPU and memory, HPA will scale. Let's say for example, in this example architecture, if you see here, there is a one pod is running. So when there was there is a spike in the network, this HPA kicked in and it has scaled out horizontally. It has provisioned additional pods also, and when there is not much traffic left, it has scaled in. So we have came back to the original state. So this is how the HPA works. Now let me just show you a quick demo of HPA before we jump into the KEDA. That will tell you, okay, why that KEDA is important over here. I need to use my laptop. Okay, you can hear me, right? Okay, fine. Now, if you see here, right, let me just show you a demo of HPA. Now, this is on AWS. So I have my own, the application running. So this application is running, is sitting behind a load balancer. This is the load balancer U1. If I see the state of the load balancer, so all the application is healthy. Load balancer is pointing to the healthy state. Now, if I go and copy this DNS, yeah. So my application is up and running. So there is no problem with the application. Now I request everyone to just focus on these terminals. So I have divided into the 4 parts. So the first left is about the queue proxy. So what it is doing, it's not doing much basically. It is going to show this this dashboard so that we can easily see. Okay, let me just log into the dashboard again. Right. So this demo I'm going to show in a specific namespace, which is known as the HPA demo. So we have various namespaces, right? So let's focus on this HPA demo. So if you see here in the HPA demo, we have within that HPA demo we have just one pod running. So if you see here, the count is one over here, and you can see that just one pod is running. So it's one by one. Now, let me show you file also, like the code which is running behind this application. So what I've done here, I've created a namespace which is HPA demo. Then I've deployed an application called my application within that namespace. And I have also specified the resource, request, and the limit. So this is very important when it comes to HPA. So without this, the HPA will not work. Then I have exposed my application using the load balancer. So that's the reason I'm able to access my application over here in a public load balancer, publication we call it. And finally, we got this HPA. So this is very important. So this is what I was referring to. So if you see here, this HPA will start monitoring this particular deployment. And the name of the deployment is my deployment. And it is going to scale somewhere between one replica or max is two replicas here. We have already seen that the only one replica is running. So when we put some load onto this application, we expect this application to scale out and have additional pod. But based on what metrics? So it is looking for this, which is CPU. This is target synchronization metrics, which is 75% over here. Now, I request now on this, if I put some load onto this, you will see the pod running over here. So here you will see the logs coming when I start bombarding this application with some HTTP dummy HTTP calls. And you will see the HPA also. So if you see the current HPA, can you see my terminal very well? Like, is it appearing? Is the pod? Okay, fine. So if you see here, currently the pod is running with a 2% CPU utilization, but we expect somewhere between 75%. Now let me just put some load to this. Now I'm using Apache benchmark, I'm trying to put some load. And the pod is receiving those many HTTP calls. And in a moment you will see this target is going to breach. The moment we breach the 75% of limit, we will see additional pods. So now it's 77%. Let's see whether we got additional pod or not. Let me put more requests to it. All right, now if you see here, we got additional pod got created. So if you see here, this is the newest pod which got created a few seconds ago. And if we go back here also, you will see the maximum pod we were expecting is 2 and the current replicas is also 2. So this is how the HPA works. Now, we'll just keep this application open and you will see it is coming down after a while. Okay, so we have seen how the HPA works. So HPA has a limitation. The major limitation with the HPA is that it only looks for CPU memory. It cannot, you cannot scale your application based on different metrics, right? So that's a traditional way of doing it. But when it comes to KEDA, right? So KEDA can scale your application. Again, it's a horizontal scaling. KEDA doesn't support any kind of VPA approach. You know, it will always scale out and scale in. So that, but it can scale based on different matrices. For example, if you want to scale your application based on some external events, let's say if you have a loosely coupled architecture where you're using some kind of message broker, let's say RabbitMQ or and all, based on the number of messages which you receive in the queue, you can scale your consumer pods. So that is one thing. Second thing is, if you want to completely bring down your application, let's say the pod 0 level, you can also use that, like KEDA for that purpose. Let's say, for example, if you have any kind of batch job processing, which you want to do it on a nightly basis based on the number of messages you receive, KEDA can be a solution for that. And not to forget, KEDA can also do in a natively using the CPU memory, besides doing the other external events. So these are the key tenets which you see over here. KEDA supports zero pod scaling, like I mentioned. You can bring down the pod to deployment to absolutely to zero. Means no pod running, completely down. So this will save your cost. Let's say, for example, if you have in your companies also, if you have the shared instances where different teams are using their own application of the shared instances, you can save that shared cost for your team by using the KEDA, because you are not going to use only CPU memory utilization over there. Then second point is, like I mentioned, it has support for various scalars. If you want to listen from the Redis scalar, you can use the KEDA. If you want to listen from Prometheus or SQS queues, you can use KEDA over there. And not to forget, KEDA also supports natively based on CPU memory as well, besides other things. So when you install KEDA, so there are reference links also. When you go to keda.sh, you can go via the documentation and install the KEDA. There are different ways, but the best is go and install via the help charts. Once you install the KEDA, so this is very important. In the architecture wise, the three major components work behind the scene. So we have metric adapter, controller, scaler. So these are respected to KEDA only. And how this components works, right, in order to understand that it has that intelligence ready. So metric adapter works as an adapter between your Kubernetes as well as your external source of events. So the only responsibility for the metric adapter is to collect the metrics and make it available for the Kubernetes in an understandable way. Then we have the controller. This is a KEDA controller. So what the KEDA controller will do, once those metrics are available, so KEDA controller will act on that metrics and can do some scaling decisions. Once it has to do any kind of scaling decision, it will tell the scaler to actually go and do the scaling. So it is the scaler is the one which is actually doing the scaling. So it will instruct, it can go and update the desired replica count via that Kubernetes API. So a scaler will not do by itself, it will instruct the Kubernetes API. Kubernetes API is going to update that desired. So you can think of scaler something like controller manager, like I talked about before. So it has to match the desired versus the actual state. So these are the three broad main components that works on the KEDA. Now, there are some better use cases. So like I mentioned, so KEDA can be used any kind of batch job where you don't expect a real-time synchronous based call. You can have an asynchronous based call also completely down, and then you are bringing up. Let's say, for example, you have, let's say, take an example of Amazon audit. Let's say if you have a bunch of orders got processed, you have the messages coming into the SKS queue. Now, if you want to run the KEDA based on, let's say, I want to fulfill the orders. If I get 50 messages, you can base on batch size also. You can run that jobs. Of course, for the servers also, you can use KEDA and find the microservices based app. If you have any kind of microservices based application, you can use KEDA, but you should not be bringing the application to completely down. If it is an HTTP based call, because otherwise it will be timed out. When a client makes a call to the server, you want to have some kind of backend call. but it can scale, of course, based on the traffic. Now, this is the final demo which I want to talk about using the SQS over here. Now, if you see here, this is the architecture which I am going to talk about. So, we have an SQS queue and the producer. So, producer is push some dummy messages to the SQS queue. Then we have a KEDA. And in this demo, you will see the pod getting scaled from 0 to n. Like, yeah, let me just show this final demo. So if you see here, when I, okay, for just to give you some background of it, so if you see here, for this KEDA demo, I'm using a different namespace, which is this KEDA demo. It's a complete different namespace over here. And if you see here, we have a deployment, but we don't have any pod running. So it's completely 0 by 0. We don't see any pod also over here. Now, how this KEDA file will look like before I execute that demo thing. So if you see here, I have created a KEDA demo namespace and I have deployed the same application, the KEDA demo namespace. Then, in order to authenticate the KEDA, see every your KEDA your metric adapter has to connect to the external sources. So in this case, it is going to connect to the SQS to see how many messages we got it. So we need some kind of authentication. So in that case, what I have done, I have created a secret over here. Then also I have mentioned the trigger authentication. So these are specific to KEDA only. And this particular authentication will have access to the SQS. And this is the main KEDA scaled object. Now, if you see here, I have intentionally commented out these things. So I'll tell you why these have been commented out. So let's say, for example, if you want to debug your application which is running using the KEDA, you don't want to kill the KEDA, the whole application. In that case, you can come and update the scaled object and make this to true. And also you can specify two replicas, like how many replica you want to put a pause. Basically, you're pausing your KEDA from scaling. So in that case, you can give these annotations. And then if you see here, this is the main thing, which is the scale target. So here in this case, the KEDA will look for this deployment, and we are saying, using the polling interval, you go and poll after every 5 seconds. And then cooldown period is 20 seconds, means before scaling in or scaling out, you wait for 20 seconds before taking any action. And then we are seeing minimum replica count as 0. Because of this only, you will see there are no application running, and then maximum replica count is 10 over here. So these are the few optional attributes which you would really want to explore it by yourself. And finally, we have a fallback. So I'm not using the fallback in this demo, but I'll explain, and that's the reason I've commented out. So let's say, for example, if somehow this KEDA is not able to connect to your external metrics, external systems, right? Let's say it's not able to connect to SQS or Prometheus to get the metrics. You don't want your application to be impacted because of that. So you need to have a fallback strategy. This fallback strategy is completely optional. You can define what is the threshold for that. Let's say any kind of consecutive 5 connectivity issue will use these replicas. So minimum 1 will be taken if there is any connectivity, metric adapter is not able to collect the metrics from external systems. And finally, we have a trigger. So if you see here, we are going to fetch the, KEDA is going to fetch the metrics from the SKS queue. This is the queue URL, and there is a batch size of 5 bits. After every 5 messages, it is going to do the scaling decision. Now let me just go and push the messages into this. Let me show you the queue also. So we have this queue for this demo purpose. If you see here, we don't have any messages currently in this. And in this application is also not running. So let me just push some dummy messages to it. And you will see over here. And okay, let me give you a walk around of here also. So if you see here, this is the scaled object which got created. It is looking for this deployment. And the deployment name is this my app KEDA. So we expect somewhere between 0 to 10 replicas, and this is the name of the trigger authentication. But the main flag which you want to see here is ready. This KEDA is active. It is able to connect to the SQS, but it is not running. Then we have the fallback, like I already mentioned. If you have any fallback mechanism configured, it will show as true. Then we have the paused. Let's say if you want to debug your KEDA object, you don't want to kill the KEDA, you can just go and annotate that pause to true. Then you can go and debug it. So let me just push some dummy messages. So I started pushing some dummy messages to the SKS queue. And you will see this active changing to true. Yeah, you will see here now the messages are going in the queue. You will see the replica has increased. The replica count has increased now. Let's see the dashboard over here. Yeah, you will see the pods spinning up based on these external metrics. And here in the queue also we can verify whether we received the messages or not. So we have got 15 messages in the queue, and hence the KEDA is able to scale the application horizontally. Yeah. So key takeaways, like what all things we have understood today. So we started with an example of Amazon.com, where we understand the importance of scaling an application, be it monolithic or microservice-based applications. Scaling an application is very important. Then we get into the different Kubernetes-based autoscaling techniques, which is HPA, CA, and VPA. Then we had a deep dive into the HPA, where we were able to scale based on CPU and memory as a metrics. And finally, we get into the architecture of the KEDA, and we have seen the KEDA in action using the SQS as an example. So yeah, these are the reference links which I would recommend, like you can go through with it. And all the source code which I've used so far, I have already pushed in this repository. So you will find a lot many infrastructure as a code, Terraform scripts also over here. Yeah, that's it. I'll just keep it for, yeah. Thank you so much. I'm open for questions.
You mentioned about sidecar design pattern.
Yes.
On the side. What is it? Explain more.
Yes, sidecar design pattern, right? Okay. I'll just go back to it. Correct. This one, right? The sidecar design pattern, right? See, technically, Kubernetes is not stopping you for putting all those containers in a single pod. In the same pod, you can have different containers. One containers for a UI, one containers for a business logic, and even you can have a database also. But that is a bad design practice because if a pod goes down, all an application will be completely down. So you better use one pod, one container is equals to one pod. Means one for UI, one for your business logic, and also you can have database also as a pod, but that's not recommended because if you keep pod as a database, right, you need to take consistent snapshots also onto the S3, or you need to sync up because if a pod goes down, all your data will be lost, right? So you can use some kind of managed services or dedicated database server in that case. Now, what happens? So this is a different thing. When it comes to sidecar design pattern, right? So few things like I mentioned in the microservices world before, that logging or security. So those are considered as a sidecar design pattern. Means from your application perspective, right? In your company also you will have different teams maintaining the infrastructure, or you as an application team will be more focused on writing the code and how you can deploy it. You may not be worried about the other things. Like for example, the logging, that will be taken care by the infrastructure team. Or security, how one microservice is able to communicate with the second microservice, other microservice in a secure way. So what you can do in that case, you can use some kind of sidecar design pattern, which you don't have to do it. If you are using some kind of service mesh or kind of other things, you can inject how the service mesh thing works, right? So it will inject by itself. You as an application will just go and deploy it, but the service mesh will do its job. It will handle the logging part. You don't have to worry whether the logging is happening or not. All you have to do is just do the standard log output. There will be daemon sets running, there will be agents running on the cluster, which is going to correct that metrics and push to, let's say if you're using the Elasticsearch or if you're using some kind of Prometheus, it will go and stream that logs. But this sidecar will help it. And it knows where that log your application is throwing. It will correct that and it will push. That is one thing. You can use the sidecar as for logging purpose. All those corner cases which you don't want to do it. Your security. Let's say if your pod A wants to communicate with the pod B in an HTTPS base, in a secured way, TLS, secured, your certificates and all. You don't want to do it, right, as an application team. Your infrastructure should take it. And how they do it, they inject some kind of service mesh, let's say linker or anything. So all those corner cases, logging, security, any kind of read-write mechanism, so these are considered as a sidecar design pattern. So in that case, you are not adding all those containers. You will see when you go and check the logs, when you open that pod manifest file running in the Kubernetes cluster, you will see multiple containers running. If you see the pod definition, you will see your application, you will see the other thing also, the logging or service mesh. That's known as the sidecar thing. Yeah, but from your perspective, you should not go and deploy multiple applications within a pod until unless it's a sidecar. Yeah, that was a very good question. Yeah. Anything else? I'm happy to assist. Yeah. Please go ahead.
Yes. So basically, hello.
Yeah.
Okay. So we majorly discussed 4 patterns of autoscaling, right? BP, HPA, CA, and KEDA.
Yes.
Now, what we have observed is basically, let's say you have made the pod bustable, right? Quality of service is basically bustable. The request is less, and the limits are more. And in that case, let's say you have put the HPA of target utilization to 75. Now, what happens is basically pod will try to auto-scale itself in the VPA manner first. Right? Let's say if the 100M is the memory CPU and it has 200M as the limit, it will try to upscale in the VPA manner. Now, in the HPA case, we take the target as 75. Now, that target is basically on which? On the request or on the limit?
So that target will look for the request one. So you have already set my, the threshold. Let's say for example, you have, okay, in a hypothetical cases, let's say you have, 4 GB, that's the limit, right? But you are allocating all in individual pods, let's say it's not one pod, it's specifically 2 pod, right? It starts in that pattern. So 2 pod, right? So if you are going anything beyond that limit, then this HP will kick in.
Okay, so let's say if I've made 1:4 as the request and limit, after the limit is breached,
Yes.
The HPA will kick in.
HP will take it, yeah.
Okay.
Yeah, you can do the HPA based on memory. So in the code which I have shown here, right? So there was HPA based on CPU as well, memory also, but I was not using the CPU level. I have mentioned as a target CPU transition. So it's an average collectively. So if you have already 2 pods running, it will correct the average of all. Then if something is breaching beyond that average, then that HPA will kick in.
So basically both VPA and HPA can work synchronously based on.
They can, but ideally it's not recommended to have VPA along with HPA, specifically if you are running for any kind of stateful. You can have VPA separate.
And the second question, let's say we have KEDA implemented over there, and we have VPA, HPA as well. Now, because KEDA is an event-based programmer and it kicks on the events, and the HPA is also there. So, which is prioritized? Let's say if there is sudden load has come up on the pod and it is going crazy out of there, and the KEDA has is there memory ready for any kind of use case? In that scenario, what will it?
I think that's again a very good question over here. And the reason why is HP will take the precedence. If your intention, if your configuration is about scale to minimum 1. But let's say if you want if your configuration talks about scale to absolutely to 0, then the KEDA will take the precedence. If you want to do something 1 to n, that's what if you see this diagram. If you see this diagram, right, this KEDA thing, HP will kick in if your configuration talks about 1 to n or into 1. If KEDA will directly handle this, if your configuration talks about 0 to 1, at least if there is a 0 reference, right, then the KEDA will do it.
Got it. Yeah. And last one, which is the tool which we are using for the Kubernetes, the dashboard, which is
So that's an inbuilt, like I'm just using.
Oh.
It's a Kubernetes native only.
native dashboard.
Native dashboard.
Follow up to that question, I was thinking that both of them would conflict with each other. So let's say
We don't install, let's say for example, if you have a KEDA already running, right? We don't go and configure HPA separately. We don't do it. KEDA will do it by itself. So in the separate namespace in the second demo which I have shown for the KEDA one, right? You will not see the HPA which I have done manually. So that's something KEDA is doing it behind the scene. Any more questions? How many minutes we got? Okay, yeah. Thank you. Thank you.
So that was a nice one on KEDA. I hope. So anyone, like how many of you here are already working on Kubernetes, have an idea about Kubernetes? Hands please. Okay, not a lot, but okay. I hope everyone learned something. And just add to that, you did mention about resources, request and limits. And over there you also talked about VPA. So by default, VPA won't come in action over there. VPA unless externally added does not work. In that case, when you have both request and limits, QoS comes in over there. And your breach limit utilization works on request as you mentioned. But your pod won't scale out. Scale out means your pod getting bigger by the scale. When you have VPA dedicated over there, usually you don't put that in production. You usually use that when you do stress testing and knowing what should be the suitable count for limit and request. Other than that, I don't think we ever use that.
There is VPA dedicated resource which you deploy.
Yes, VPA is something you have to deploy as a different thing and run accordingly. It's not something inbuilt. So requests and limits are for QoS. So that's what QoS is. In short, if I explain you, it's like priority. on when your pods come in, how they get evicted or how they're scheduled. So that's what we have for.
So the best practice would be to make it guaranteed always.
Depends on your application. There is no best as such best practice. It depends on what that application does and when is it required. Depending on your requirement, when you list out your document, of course, when you go to this microservice architecture, you need a full documentation on why and what. Over there, you mentioned, okay, I need this on priority, I need this not on guaranteed, because we have 3 options of QoS depending on what values you set. So it's up to you how you play on it. And Satyam,
Yes,
you can take over.
I think you can call the speaker.
So anyone would like to come over here and explain, just define what KEDA is?